Because a Banach field is a topological field which is complete. As a metric space. Examples, I told you that we have R with the usual absolute value, let me call it like this. We have C with this, and these are Archimedean, because the ultrametric inequality does not hold for these two particular absolute values. But other examples are Q with the periodic completion. This is by definition a Banach field because I am completing. It is a topological field with evaluation induced by a metric or a topology induced by evaluation, and it is complete because I am completing it. Okay? And I have a periodic field for every prime. So I have too many fields which are non-Archimedean. Okay? Now, if I have a Banach field, I can try to do analysis. I can try to do convergence sequences, analytic functions, and maybe I can have a non-Archimedean version of real analysis and complex analysis. And this was a question that appeared in 1940s. People said, okay, you know what, we have the periodic numbers, it is a complete field, so it has no holes. What if can we invent a theory of analytic functions over the periodic numbers? So, Mark Krasner in the 40s asked this question. Is there a theory of periodic analysis? This was Mark Krasner. (1940s). And let me tell you that this sparked one of the biggest branches of mathematics alive now, which is non-Archimedean geometry. This evolved in what we know now as non-Archimedean geometry. Also goes by the name of rigid geometry. And again, this has many applications in number theory. Now let me show you a little theorem to explain the differences between Archimedean analysis and non-Archimedean analysis. Recall, non-Archimedean means the ultrametric inequality holds. A theorem from calculus 1. You have a series, and you ask about criteria when this series is convergent. One of these routes is true in real analysis and the other is false. Which one is true and which one is false? So we have this route and we have this.
One is over is true and below is first.
This one is true.
Yes.
If the series is convergent, then the general term should go to 0.
Yes.
I am telling you that in the non-Archimedean analysis, Banach and non-Archimedean. I am telling you that the topology of non-Archimedean fields makes the other implication true. Let's prove it. So, I need to assume that the limit of the value, so this case, if it is Banach, it has an absolute value which satisfies the ultrametric inequality. So, I need to show this second one. I will assume that the limit of the general value goes to 0. And I must show that the series is convergent. So, in order to do this, I need, perhaps I need another hypothesis, I don't remember. I need to measure, I need to estimate the sum of the cube, right, of the last terms after a finite number. And what I need to do is, yes, so using this hypothesis, it tells me that for every epsilon, there exists an index such that the absolute value minus 0, which is the limit, is smaller than epsilon for every I bigger or equal than, let's fix this.
Yes.
Right? And since 0, 0, I can erase it, and it happens this, right? So, I want to show this, so I will separate the sum into, I will give this epsilon, and I can separate this sum in two pieces, right? The first and 0 and the rest. So, I think that I can't remember exactly the proof right now, but after this hypothesis, the idea is to apply the ultrametric inequality to show that this holds. Sorry, I don't want to lose time. Maybe next class I can give you the proof, but believe me, this result is true. Okay, I won't pursue the proof, but it goes along these lines.
Can we generalize ultrametric inequality?
Sorry?
For the nth term and n plus 1 term, so that we choose max only one term.
Yes, that's the idea. We should pick some max.
Yeah.
But let me bring the proof tomorrow, because I wasn't planning to do this right now. Okay, sorry about that. But what I want to highlight here, what I want to show you here, is that non-Archimedean analysis is essentially different from traditional analysis.
I think the proof is clear. I think, and that we choose any max term, and AI is less than epsilon for all I greater than or equal to n naught.
Yeah.
So it means that if their sum is finite.
Because you say that we are bumping here all the elements that
Yeah.
come after this and 0.
Yeah.
So we can choose a maximum among all these
Yes.
possibilities, and then in all the previous terms.
Yes.
Yes, that's a proof.
This will be less than or equal to that maximum, and that maximum will converge to 0. So the
Yes, thank you very much. So the proof is left as an exercise to you, just to fit the details, but the proof is already there. We need to take the maximum. But the key is the ultrametric inequality, right? Okay, so let's go back to the question of Cristhian. Now let K bar be a Banach field.
I have a question. Can we refine valuation topology? That first we define Z-script topology to valuation topology. Can we refine valuation topology so that we get a nice topology?
Very good question. I think that the answer is no, because of the theorem that I put yesterday, that every nice topology which you have and respects the algebraic operation on a field should come from a valuation. So the theorem says that if K is a field and tau is a nice topology on K,
yes.
So nice means that it is Hausdorff and the operations are continuous under this topology, then this topology should come from evaluation. And in some sense, I showed you that any evaluation satisfies the ultrametric inequality, so it is going to induce a totally disconnected topology. So the answer is no. We need to be more smart than that. And that's what John Tate made with rigid geometry. If I have some time, I can explain something about that. Anyway, so if I have a Banach field, then I don't have poles, so I can define analytic functions. What is an analytic function? Do you know the concept?
Yes.
Do you know the concept of analytic function? So, a map that goes from K to K is analytic at a point Pk, if and only if, what happens?
It is differentiable at some neighborhood of this point.
Each.
There is an open set
Yes.
around P such that every point there, if I evaluate the function, it's represented by a forward series which is convergent, right?
Yes.
Yes,
That's
yes,
another equivalent definition.
Yes.
This is the general definition of analyticity. So this map is analytic at P if and only if there exists a radius such that for every cube in the wall centered at P of radius R, the function evaluated at Q is some coefficients, and here is P minus Q to the I equals 0 up to infinity, and this should be convergent, right? For every point inside the ball. This is being analytic. And if K bar is R or C, we recover real analytic and complex analytic, but also for p-adic. This, if I put here the p-adic numbers is a Banach field, and I can define p-adic analytic functions. But the problem is that the topology is going to make that the class of analytic functions from a p-adic set is useless. So there is a famous example in which you can define the closed set as two open sets. So let me finish with this. This definition works with reals, complex, p-adics, and in general any Banach field. The problem is that the topology, if the field is non-Archimedean, the class of analytic functions is not interesting. Example, you don't have analytic continuation. And for this example, let me show that the boundary of the closed unit disk is open. So, I showed you that the closed disk was open, right? This is what we did before the break. I picked Y here, I constructed the ball of radius R, where R was smaller than 1, and I showed that the whole ball was contained inside the disk. What is the topological boundary of this? It is the unit circle, right? So the boundary of the closed disk is just x in K such that the norm of x is 1. Like usually we do in complex analysis or in real analysis. If you take the unit word, this is the open disk, centered at 0, radius 1. If you close it, then you take in consideration the perimeter. And if you take the topological boundary, you take away the inside. And we can show that the topological boundary in this case is closed, right? I will show that in the non-Archimedean case, this is open. And what do we need to do? The same thing. We take a point here, and we show that there is a positive radius such that the ball around this point of that radius is contained here. But the principle is the same. Let me take R strictly smaller than 1 and strictly bigger than 0, and let me consider the open ball centered around Y with radius R. My goal is to show that this is contained here. Sorry. So I need to take a point here, and I need to show that the norm is 1. Let me see if I can do it. maybe the same trick is not going to do it. So I need to show that the norm of Z is 1. Yeah, I think that the same tree is not going to do it. Okay, so maybe yes, because y is here,
Yes.
so the norm is 1, right? So let me do the same trick. No, it's not going to do it because this is less than or equal to max z minus y plus y, yeah, and z minus y. Or maybe I can take r equal 1, right? Directly. So if I take y r equal 1, then this norm is 1. No.
As if we take 1 or less than 1, in both cases z minus y should be less than 1.
Yeah.
So we get y is equal to 1.
But I want to show that the norm of z here 1 is 1. So I start doing the same thing, minus y plus y, and I just, by the ultrametric inequality, I just get here smaller than, and here, even if I put r, this is 1, and this tells me that z is less or equal than 1. But as you told me, this has to be bigger than 1 to be equal, right? Okay, so tomorrow I will bring you the proof also for this. So I have 2 homeworks. The first one is to show you the convergence, and the second one is to show that the boundary of the sphere, the periodic sphere, is closed. The periodic circle is closed. But believe me, so if I have shown that the boundary is open, then I can describe this open set as union of 2 open sets. For example, I can put this open set as the open set, which is the classical strictly less than 1, and those which have norm 1. And I showed that this is open. Since the topology is metric, this is open by definition. And this is my homework, to show that this is open. But then I can decompose a function in this open set as a locally constant function equal to 0 here, as a locally constant function equal to 1 here. And this is a function which is not analytic, but it satisfies the properties of, it satisfies the properties, but it is constant in one open set and constant in another open set. So tomorrow I will, let me see what time is it? Okay, you have time. So what I'm telling you is that the problem with the topology translates the fact that the class of analytic functions that I can define here do not satisfy analytic continuation and do not satisfy the maximum principle. So even if I can define analytic functions on the p-adics, the theory that results is not good. But this was Krasner's work. Mark Krasner defined this, and he was working on this. And when he saw these problems, he stopped working. But afterwards, an American mathematician called John Tate.
I have a question.
Yes.
Can we define analytic function in such a way that it also preserves the analytic continuation so that we can work again?
This is what I'm going to ask. So there is a solution to this problem, but it's different. Yes, there exists a theory of analytic functions, but we need a new paradigm. So the answer, the short answer is yes. And the answer was given by Tate, which is an American number theorist. So in 1952, John Tate gave an answer to the theory of QP analytic function. His theory is called rigid geometry. And rigid geometry gives you a theory of p-adic analytic functions, but there is a price to pay. And the price to pay is that you cannot consider all the open sets generated by the metric. You need to consider certain sets which are called affinoid. So this comes with a price to pay. Namely, we have to restrict the amount of open sets. In QP to those that are called affinoid. And just to finish this session, let's make a comparison between what we did today. I erased the topologies, but I can rewrite them and put the rigid geometry where it belongs. So we said that the discrete topology sits here. Then the Zariski topology sits here. Then the evaluative version, the evaluative topology sits here. We have this, this, right? And there is a new topology called the rigid topology, which at the same time refines Zariski, but you don't take it refines discrete. Yes, the discrete, of course, is at the
Finder.
Yes, this is contained. Every topology is contained here, right?
Yes.
And here, what you do is that you take these open sets, but you take away some open sets. You don't consider all of them. So you have this order. This contains less open sets than this. And it is called rigid because precisely you have too many open sets. What you do is that you take away a right amount of open sets such that the concept of analytic works. Okay?
Yes.
So this was Tate's idea. okay, I will throw away some concepts, some open sets from the p-adics, such that the concept of analytic function over the p-adics makes sense. The problem, and with this I will end, is that this is no longer a topology. It is what we call a Grothendieck topology. So Grothendieck topologies are not topologies. But they have a good concept of analytic function in this case. Now, it appears that I took all this day to talk about topology. What is tropical mathematics? It's precisely the ultrametric inequality is tropical. And in fact, rigid geometry has many connections with tropical geometry. For example, the tropicalization of an analytic curve is a tropical curve. I will finish with that, and maybe if there is time afterwards, I can talk to you about tropical curves and tropicalization. The problem is that this is very technical because we need algebraic geometry. But rigid geometry has connection with tropical geometry, and the statement is that the tropicalization of analytic varieties rigid in this sense are tropical varieties. And the link is precisely the ultrametric inequality. So, non-Archimedean geometry, that's another name, rigid or non-Archimedean. Is the hard part of tropical geometry. Tropical geometry, tropicalization, in which the drawings, if you have seen a tropical curve, let me draw a cubic for you. If you go to YouTube and you put in the search bar tropical curve or tropical geometry, you are going to see something like this. And people usually tells you that this is the Zeno set of a tropical polynomial, which is just combinatorics. But what I want to tell you here is that this is a shadow of an analytic variety of a non-Archimedean field. So in some sense, we are doing non-Archimedean analysis similar to what we do in the reals or in the complex numbers, but now over other fields, which may be interesting for number theory or for physics or for other things which are not classical. I think this is the end of this day. Thank you.